Hello. Let's start the presentation. My name is Ming Lei. I'm working for Canonical. This presentation is about Virtio block multi-coin conversion and QEMU block related optimization. The first two parts about Linux block multi-coin background and Linux Virtio block multi-coin support. The other three parts about QEMU side. Two interesting optimizations are presented. Then it's Virtio block multi-coin support. The last part is some related work in the near future. Linux block multi-coin is introduced for supporting high LPS SSID storage. Why is the multi-coin introduced? Because the older block subsystem of Linux has a biggest bottleneck. It's request to coin lock. This coin is required in lots of places. Linux block multi-coin introduced two levels of coins. The first level is perceptual software coin. With this level coin, AIO schedule, AIO merge, AIO tagging, AIO accounting can be done in this level coin. Another level coin is hardware coin. It's also called dispatch coin. With dispatch coin, requests can be submitted to the hardware. So with this two-level coins design, the old bottleneck problem is fixed. Currently, the non-block virtueue block and the scarce middle layer and MTIP32XX drivers have supported multi-coin already, and the loop, NVMe, and Zen is being reviewed for the multi-coin support. The virtueue block multi-coin is merged to Linux 3.13. With multi-coin support, the throughput can be improved, especially for some faster devices. It don't need the QEMU change, but it still uses single virtual coin. That means, but because the single virtual coin lock is required in both submit paths and the computation paths, so the scalability can't be good. It may be not enough for some fast devices. So the multi-dispatch and the hardware coin patches are merged in 3.17. The idea is very natural. It's just to map the virtueuse virtual coin to block multi-coins hardware coin. It's very natural. And because the virtual coin has some kind of hardware feature, like the interrupter and the enqueue. So there is no bottleneck from VM anymore. But this feature needs QEMU support because the MQ feature is added to the virtual block spec. The maintainer has approved this change will be added to the virtual block spec. When I developed the multi-dispatch quick patches, I wrote some simple multi-vertical patches against the QEMU2. And with this simple conversion patches, throughput get improved about 30%. But virtual, but maybe it should be pre-2.1. The virtual block switching to the QEMU block layer. With this change, I found that the throughput becomes not good as before, even with the multi-virtue conversion. So I started the investigation. It's a based virtual dataplane IO module. It's a single IO thread. Actually, it's in the high LPS block storage situation. The IO thread can be thought as compute-bound type of thread. Before I present the optimization, let's see the benchmark environment. The VM configuration is quite common. It's a quad-core with 8 GB RAM, and I just use the non-block device as a backbone because its IO access property is very similar with SSD. Also, the backend file is transferred to the QEMU block layer, at least for the same type of backend. I also tried the loop block device over file on TMPFS. The result is even better than non-block. The QEMU is based the current 2.2 The host is a Intel Xeon server with Ubuntu Trust and 16 threads, 22 GB RAM. I use the FIO to measure the throughput boost. Two jobs are used to test a single virtual case, and 4 jobs are used to test a dual virtual case. IO engine is labeled AIO, and use the direct IO. The first optimization is about IO batch submission. Before I explain IO batch submission, let's see the IO submit system call first. This system call can be used to increase arbitrary number of read or write requests at one time. The request can be submitted to one file or more than one file. So why don't let IO submit to handle more requests? So then the calling number of IO submit, it's a system call, can be decreased a lot times. Also inside the IO submit, kernel will hold the per-task IO plug. With this plug is hold, the IO request can be handled as with batch or merge. Actually, this kind of feature is used in virtual-blk dataplane from beginning, but looks no one noticed its power before, and just thought it's a natural way to handle this request. Long time ago, I compared LQVM with QEMU and found there is big difference between the IO block performance. So I noticed this difference. It's removed when switching to QEMU's block layer. The two interfaces, it's a general interface, IO plug and IO unplug are introduced for handling IO as a batch. Actually, there is a one IO queue behind the idea. Currently, the IO queue is a block drive state, but it should be extended to AIO context. Because, as I said, it can be used to submit requests from to more than one file. Also, it has wider usage. Can be used for other block devices in case of native AIO, either dataplane or not. One typical use case for submit I/O to more than one file is multi-run SCSI. Oh, let's see this table. It's the test is done with another optimization is enabled. It's a single virtue-queue. The first column is a bench type name. The second column is throughput tested without I/O as a batch. The third column is throughput with I/O batch enabled. So the last column shows the improvement percentage. At least for the first three benchmark, the improvement is quite obvious. I have done some profile inside QEMU to see what's behind the big difference. Use the simple trees. The first row is the average number, request number per I/O submission. Once I/O batch is enabled, we can see more than 26 requests can be submitted in one I/O submit system call. The second row is the average request number handled in one time. It's handled in one virtue-queue host notifier handler. About half requests has been cut. This number indicates that the time consumed by host notifier handler is increased by submitted I/O as by batch. The third row is the computed average time for submitting one single request by QEMU. With this calculation, we can find about 23% get improved. This is just the time taken in the submitting pass. Why is the write isn't guide much improvement? It's the multi-write makes the difference, because multi-write will use the write merge to merge the sequential writes aggressively. From this table, we can see that it's the second row and the third row. The second row is the merged request number. The third row is the average request number handled in one time, like this one. This two row also indicates the time taken by the host notifier handler. An interesting point about multi-write is that the more time, the less time the handler takes, more requests get merged. That means the handler, more slowly the handler, more requests get merged. It's still a kind of a batch process. But even though, because of I/O submit as a batch, we still can see there are some increase about the average time for submitting one single request. The second optimization is about the bypass coroutine. Coroutine is used widely inside QEMU, and especially the block layer. But in my test, in this test, we can see at least for some high LPS device, the cost isn't cheap. For example, about more than 300 100 nanoseconds is introduced for calling one single function. This function is just a loop, so the cost doesn't represent the cost from switching stack. Then it's easiest to figure out that if the block device's IOPS is 100K, the throughput may decrease, at least it decreases about 3%. If the IOPS is more, the throughput will be decreased more. So a natural idea is to bypass the coroutine for some, at least it's possible to do that. The previous virtueue dataplane doesn't use coroutine. But it just supports the raw image with some constraint. WC is disabled, no, don't support SCSI. So let's see the throughput improvement with bypass coroutine. This test is use the Paulus patch. It's a fast path to bypass coroutine. I've submitted the patch to Mirlis, but that version is not good as Paulus. It's still a single virtue-queue, but with IO batch submission enabled too. From this comparison, you can see there are still lots of improvement in throughput. But for write, it's still a bit special. It's still caused by the multi-write merge. And the idea is similar with before. The handler is slower. More requests get merged. It's like the Linux blocks some IO scheduler. Also have done some perf on bypass coroutine. The first perf state is without bypass coroutine. The second is a dirt with bypass coroutine. So we can see both the L1 decay load misses and the branch misses, the percentage get decreased after coroutine is bypassed. Even the absolute count is decreased too. The Paulus patch is quite direct. It's a bit simple. It's just if we can do that, just bypass. This data from the second perf data is enables the quad virtue-queue. And this time, another count can be found. It's instructions per cycle. This number is increased. About 7% is increased. So with bypass coroutine, even we can see the CPU runs code quickly. That may be because the logs binlog on VirtQeue. So let's see the QEMU Virtio-blk multi-virtue-queue support. There are two cases suitable for the multi-virtue-queue support. The first case is that there are lots of I/O from application. Concurrent I/O. It's concurrent I/O. It's very natural for read because read is synchronous, and it's a common case to read from different tasks processes. Also, the second case is that if the block device, the speed is very quick, single virtue may be not enough. And in the patch, it's very easy to multi-virtue. It just pass the number of queens parameter, like the virtue-scarce case. It supports both dataplane and non-dataplane. The current implementation is quite simple. Just handle all requests from all virtue queens in one I/O thread. Once the host notifier event comes, the code marks their request for this queen and schedule about half to handle this request. With this simple mechanisms, the request can be handled as a batch too. It also can make the I/O thread at full loading. Also in the future, maybe more I/O threads can be introduced for handling requests from multi-queens, such as more than one virtue queens handled or mapped to one I/O thread, like Stephen Morning's presentation. It's just a draft idea. Okay, let's say the scalability improvement with multi-virtue queen support. The first test data is with the single virtue queen. The second table includes the data from two virtue queens. And the second row, second column is the FIO test with two jobs. The third column is the test jobs with four test jobs. So in the single virtue queen test, we can see the throughput decreased a lot. It's because the virtue queen log condition. But once the queens becomes two, the throughput get little increased. But for write, it is still special. It increased a lot. Why the write get so much improvement? It's still because the multi-write merge. With write merge, the I/O thread has enough CPU to handle more requests. So with multi-queen can help the I/O thread at full loading, and the throughput get lots of improvement. But for the first three bench, the I/O thread CPU utilization is close to 100%. So there's little improvement on the throughput. Basically, I observed multi-virtue queen can have two situations. The first situation, if QEM's I/O handling is slow, the request can be exhausted inside VM because every request queen has the queen depth requests. If the request has been exhausted, the I/O path will sleep inside the block multi-queen. For example, multi-queen can improve throughput about 30% if bypass coroutine is disabled. Just not use the bypass coroutine. If the QEMU's AIO handling is too quick, a request from a single virtue can't catch up with QEMU's AIO scaling, AIO processing. Multi-queue can help this case too. For example, QEMU2 can get much improvement with just multi-virtue patches. This is the current status. All these patches are in this gate tree with linux-aio fixed patches and bypass coroutine patches and the multi-virtue support patches on Virtio-blk. The AIO patch, fixed patch is needed because it needed to handle the again cases. If there are requests from more than one case, the AIO events aside, the original AIO events isn't enough. So we have to handle the again case. The first patch, as I said, it's from Paulo. But as Paulo said, it can be a start, but not much. The multi-virtue patch still depends on the AIO fixed patches. There are some draft idea for some very for some future work. The driver AIO plug and the AIO unplug interface can be used to other blocks device too. If they want to use the Linux native AIO, this AIO submit as batch can help to improve throughput. Can be extended to some AIO in batch to multiple files for multi-scarce cases. Even the virtual scarce block can use the similar optimization tool with the virtual scarce already have the multi-virtue support, but the VM's driver. Current VM's driver is just to use single queue, at least at the same time. It needs a scarce middle layer support. Someone is working on that. It will be ready soon. Also, maybe it's better with the virtual scarce dataplane with the AIO thread. These references. So that's all. Any questions? Oh, please.
You said that coroutines are very expensive. Have you looked closer what is really the cost? I know that slot context actually does two system calls to read and set signal amounts. I'm just asking myself if you really need that, if you could just switch registers, because we know that every context has the same signal mask. So that might be some. Well, it sounds good and hacky, but
it's already done, and actually it's not just an optimization. You need it because the CPU threads have different signal mask than the AIO thread, and coroutines can jump from one thread to another.
But doesn't the CPU thread use the KVM signal mask?
No, it's like the signal arm. Kernel doesn't need it anymore, but still it's it's, for example, not in the signal mask of the AIO thread, and it's in the signal mask. Or even like SIG-term is in the signal mask of the AIO thread.
Okay, so we really need you to save and restore.
Yes. No, we need to not save it and restore it. And it's already done, and it's necessary. It's not
it's a bug that we're doing this now.
Oh, yeah.
No, we're not doing it because otherwise everything would break loose. So we are doing it like you proposed, and we really need to do that. So it's not an optimization. What you proposed is what QEMU has to do and is already doing it. No system calls, otherwise have would break loose.
Well, it's for context.
It doesn't do sub context. It does jump and not jump.
under the hood, aren't we using sig long jump?
Sig long example, you can choose whether to save or not.
Okay. So trust Paula.
Yeah. So then the question remains: have you found out why coroutines are so expensive? Because it could be cheaper than threads.
I highly doubt it's related with the switching step, because I checked the system call calling with between the two keys. There is no lots of changes between system call. Any questions? Please.
I have a question. These measurements for bandwidth and different measurements for tracing measurements of performance, but I haven't found any performance evaluation results for latency for end user application. So do you have it? Because it's important. If you're batching something, you definitely increase latency.
I know. The latency is increased a bit in my test, but I didn't prove that. But it's easy to. This test can be easy to reproduce. Anyone can do that. The patches are ready, and the test is easy to do that. Okay. What's the time? Time out. Okay. All right. Thank you very much.